Good morning, ladies and gentlemen. Welcome. This is the first fight of the Brazilian Physicists Tournament. This is room 1B, and we're going to have the fight between two teams from USP and Unicamp. First, I think it's nice for us just to present the members of the jury. So, if any of the jury members would like to present themselves, please go ahead. Just so we, everybody gets a little bit more acquainted. So, please, Dr. Claudio, just say where you're from and what you do, just a little bit, so people get acquaintance with your field and in general.
Hello to all. I am from the Federal University of Rio de Janeiro, and I work with antimatter, anti-atoms and atoms and molecules and ions and lasers and things like that. Okay, and it's a pleasure to be here for the second time, and looking forward to seeing the creativity of the students in solving these interesting problems.
Hey, thank you. Now, next one could be Antonio.
Hello, good morning to all. My name is Antonio. I'm a professor here at the Federal University of ABC region in Santander. I work mainly with laser spectroscopy and optical trapping. And it's a pleasure being here again. Thank you.
Thank you. Now, Alexandre, please.
So good morning, my name is Alexandre Rocha. I work at the Instituto de Física Teórica at Unesp, Universidade Estadual Paulista in São Paulo. And I'm a computational physicist working in condensed matter and material science, mostly optical and electronic properties.
Thank you for being here. Now please, Ian Braga.
Hello, everybody. I'm Ian Braga. I'm doing my doctorate at UFMG, and I work with stochastic process and game theory, studying evolution. So I wish you all good fight. There will be no losers here today.
Nice. Now, please, for last, Professor Ubirajara.
Hello, everybody. Good morning. I am Bira from UFMG. I work with biological physics, and that's it. I hope we have a good fight and see how you guys are doing these nice problems. I'm here for the second time. This time with a team in the other room that will also be nice. So I hope we all have a good time and enjoy these fights.
All right. Thank you so much, all the jury members that agreed to be here today. I'd like to apologize for the delay in the starting of the fight, just because we had some broadcasting issues.
Yeah.
But
can I present myself?
Oh yes. There's also.
Yeah.
Oh yeah. I was always forgetting.
Okay. My name is Jerun. I'm a professor at the Federal University of ABC. And I work with material science. It's a pleasure to be here. Okay.
Yeah, sorry. I put everyone in order. I forgot one and at the last. So sorry.
No problem.
Professor, I knew I was forgetting someone. But okay. Well, I think I'm going to also ask the teams to present themselves. So in this room, we have the team from University of Campinas and University of São Paulo. So if the team from Unicamp would like to present themselves, just saying your names or something like that. Yeah, go ahead. Please present yourself.
Hey, everyone. Good morning. I'm Leonardo Falabella from Bragança Paulista, and I am the captain from the team Unicamp. Álvaro, do you want to present yourself?
Yeah, sure. My name is Álvaro.
I'm an electrical engineering student at Unicamp, and I'll be starting my second year this year.
I am Adriano. I'm
Oh yeah, we were hearing Adriano twice, apparently.
My name is Adriano, and I'm doing physics at Unicamp, and I'm in the last semester.
Hello, I am Lucas, and I'm doing computer engineering in Unicamp.
Hello, I'm João Pedro Minquilo, and I'm studying physics at Unicamp. I'm starting the 4th year.
Hello, my name is Gustavo, and I'm a grad student at Unicamp on my 3rd semester.
Cool. Thank you all, the teams from Unicamp. I mean, all the members from Team Unicamp. Now, team from University of São Paulo, if you'd like to present yourselves, please.
Thanks, Matheus. Hello, I'm Lauro. I just entered in the graduate program in University of São Paulo Physics Institute. And I would like to also invite my friends Bruno and Matheus to present themselves.
Hello everyone, my name is Bruno. I'm an undergraduate physics student in the University of São Paulo. I'm going through my 3rd year, and I wish you all a great fight.
Everyone, good morning. My name is Matheus. I'm also starting my 3rd year studying physics at the University of São Paulo. And I wish you all a good fight and a good luck.
All right, thank you so much. Now that we have everyone presented themselves already, we will start with the fight. So this is how it goes. First, we will participate in the captain's fights. So again, just reminding, what is the physics fight? What is the captain's fight for? So the captain's fight will decide who will present, who will choose to present first or second during the fights, and that means the team who wins the physics fight can choose if they will present first or oppose first, and then obviously the other team will become the will become the other role. Okay, so first let's start sharing my screen. Obviously, I shared the wrong screen. Now we prepared these slides for the physics fights and for the captain's fight. So let me just share everything. Everyone can see our screen. I think so, right? So this is the fight between Unicamp and USP, as we just said. And let's start with the captain's fight. So just reminding everyone, the captain's fight goes as it follows. I will place one question on the screen, and the captains of the teams, again, just to identify, please, the captain of the teams, should identify themselves. So who are the captains for Team Unicamp and Team USP?
For Unicamp, it's me, Leonardo. Fala.
Okay.
I'm Lauro, and I am the captain.
Yeah, okay. So Lauro and Leonardo will be the people participating in the captain's fight then. So just reminding you of the rules. You also have the clock here on the screen. So please also place the clock here. Place the clock beside your screen, so you know exactly how much time you'll have. So the thing will go as it follows. I'm going to place a question on the screen, and then the captains will have 3 minutes from the time I finish reading the question until I say the clock to start to solve the problem. Okay, and of course, like they must solve on their own, just the captains themselves. Okay, so if there were no communication with our teammates, that would be desirable, because that's how it goes on the international stage as well. So no more talk. Let's just start. So the first problem in the captain's fights is pool pipe Amazon. The Amazon basin is the part of South America drained by the Amazon River and its tributaries. The water flow rate of the Amazon River towards the ocean is the highest in the world. Now, suppose we want to create a huge pool with the same surface area as the state of São Paulo and at a depth of 1 meter. How to plane and waterproof this area is out of scope. The question is the following. How much mercury progressed on this orbit, on its orbit, in percent, when this pool is completely full, assuming that we use a pool pipe with the outflow of the Amazon River? So you have 3 minutes and you can start now. Also, captains, when you have the answers, please just send them in the chat. You have 1 minute. You have 10 seconds. 5, 4, 3, 2, 1. Oh yeah, you can instead of trying to show. Yeah, okay. Let's see. Could you please just write it on a chat? I think it's more organized. But I see that Team Unicamp put 30%. And the team from USP 73.312%. That's pretty interesting. So let's see. So let me just organize here, put it on the chat for everybody. So when you come, put 30%. And USP, how much again? Sorry, it's 73 dots 312%. Just to register. All right. So let's see, the correct answer for the captain's fights is, so the orbital period of Mercury is approximately 88 days. The flow rate of the river is approximately 209,000 meters squared per second. The surface area of São Paulo is approximately 248,000 kilometers squared. So that the pool's total volume in meters is approximately 2.48 times 10 to the 11th meters squared. Oh, sorry, meters cubed. How much time is needed? Then you just calculate knowing the volume and the flow rate. So approximately 13,745 days. So finally, the orbit progress is this time divided by the orbital period, which gives us approximately 15.62. Okay, so I believe that team Unicamp was the closest one to the response, even in log scale. I just confirmed that. Oh, I don't know. Wait, let's see. Oh, yep, that is correct. So, so Team Unicamp will be the one to choose whether they would like to present first or present second. So, Team Unicamp, what is the role that you choose, please, the captain?
We choose to start opposing, please.
All right. So the team from Unicamp will start opposing. And Team Moose will start reporting a problem. All right. So, oh, okay. I'm not sharing anymore, so I can go to. Let's see here, just for me to keep following all of the steps closely. All right. So, the team from Unicamp now can challenge Team Moose in one of the problems. So please go ahead.
We would like to challenge USP to present smashing spheres.
Challenge rejected. Tactical rejection.
Okay, tactical rejection for problem number 1, smashing spheres.
We would like to challenge USP to present the problem air bounce.
Also a tactical rejection.
We challenge USP to present physics of math.
Tactical rejection. Yeah.
We challenge flat Earth. we challenge USP to present flat Earth.
Oh, flat Earth. Okay. All right. So just remembering that USP has already 3 tactical rejections. Yeah.
That's a tactical.
So sorry, Laura, did you say something?
Yeah, I said that we will use our 4th tactical rejection.
Okay. Just reminding also that teams have a an internal rejection as well. Just reminding everyone. But yes.
Okay, so this was a permanent rejection, just to clarify.
In the first round, we can use 4 tactical rejections.
Oh, okay. No, yeah, of course. Just to clarify what you choose. So we challenge USP to present electrostatic lighter.
That's a permanent rejection.
Okay.
I'm sorry, I didn't hear you.
We choose a permanent rejection for electrostatic.
Oh, okay. Thank you. Sorry.
Yeah, people are just saying that Laura's microphone is a little bit low.
Yeah.
So, but yeah, just try to come
Okay,
closer.
so we challenge USP to present problem 8, droplets and fingerprints.
Challenge accepted.
Nice. Okay, so it'll be problem 8. Let me just
Droplet
go
fingerprint, is it?
Yeah, droplet sandy fingerprints. All right. So Team USP, you have a couple minutes to prepare yourselves. Let me just be exact and tell you how much that is. I think you have 3 minutes to prepare yourselves to get everything set. It's actually 5 minutes, so you have 5 minutes to prepare everything. Yeah, you can start the clock too. While the team USP prepares themselves, I would like to just read on the problem. So problem number 10, droplet sandy fingerprint says that when droplets fall on a surface covered by a layer of sand, interesting patterns are formed. Study the formation process. What parameters of the droplets can be inferred from the resulting crater? So that's problem number 10. Seems a lot interesting. A little bit with geology, who knows? I don't know. But interesting problem that will be presented by Team USP soon. So yeah, whenever you're ready to share your screen, Lauro, you can do it just for us to check also everything. So, or the person who presents, not exactly Lauro.
Hey, Mateus, I need to be able to share my screen.
Oh, yes, sure. Well, who's, well, oh my God, this is an interesting development. Wait, let me just check.
Lauro, can you test your microphone just to see the volume, please?
Are you hearing me well? Is it better now?
Yeah, it's better. Thanks.
Okay.
If you could try to increase the sensibility, maybe, of the mic to help.
Yeah.
But
and also, Lauro, you can also try it now. Now you're also the co-host of the session, so I think you'll be able to. To do it.
Let me try. Yeah.
Nice. I got a little scared because I was not able to choose you as the host because I was not the host. The host is Henrique, so I got a little scared. But now everything should work on as previously.
Are you seeing my screen?
Yes, we're seeing it. Would you like to test just the change of slides to see if it's good? But I think it should work fine. Like,
okay.
Yeah, cool. Yeah, it worked. So problem 10 or 8 of our tournament. The reporter has 10 minutes to present their solution, starting now, please. Go ahead.
Hello, everyone. My name is Lauro. I'm from the US Big Team. I'm going to present to you our development and exploration on the problem number 10 of the international list, which is droplet sandy fingerprints. So the statement of the problem present two main questions to the following phenomena. When droplets fall on a surface, like in this figure, covered by a layer of sand, interesting patterns are formed, as you can also see here. Study the formation process, which is the first goal, and also answer this question, which is what parameters of the droplets can be inferred from the resulting crater. First, the droplets fluid was not specified, and also about the layer of sand, we can clearly vary the density of it, the size of grain, so all these parameters will be explored. So I'm presenting to you the experimental apparatus we used to produce some interesting results on how the height of the which we drop the droplet varies with the influences in the diameter of the formed fingerprint, and also how the literature also studied this problem using a very fancy apparatus, and we will compare them and also show how they are how they answer the questions of the statements. So it is important to notice that for the experimental apparatus, which is used in literature, a laser is used to by this method of using reflections and fraction, study the formation of the fingerprint and also the whole shape with a very nice precision and accuracy. One of the goals of this presentation is to present to you the possibilities of this in studying this phenomenon, and various patterns can be observed when a droplet is hit a sand layer. Here I show some of them in a phase diagram, which is which you can see here and which are presented in different colors and symbols in this plot, which varies the height which we drop the droplet and the grain size, which is also an interesting parameter. So in the formation process, we can point out two main forces which allows these different patterns to be observed, which are the surface tension, being able to allow sandy penetration, and also cohesion force, which influences on the fingerprint shape. And the interplay between those forces will cause each pattern observed. Well, we can immediately observe three types of fingerprints as shown in this figure, which call truffle, where the cohesion force is very important, which is this first one here. The donut, where it is medium, not that much important, and the pancake also. While the cohesion force, which is responsible for maintaining the sandy grains together, are that much relevant in each of these formations. Well, on the other side, the surface tension, which is important to depth penetration, it's not that important in the first one, but it's more relevant in the second one. It's more relevant in the first one, not that much in the second one, and still less in the last one, the pancake. So these two forces then in this interplay are responsible for each formation of shape of fingerprint. Well, the parameters which can be varied are the initial height or impact speed, which are related, of course, the final fingerprint diameter, which is this DC here, the fingerprint depth, which is represented by Z, and the bulk sandy density or grain size, which you call finite or just grain size. First, the initial height or impact speed and fingerprint depth. In this figure, the main of the showing the shape of the fingerprint, the main aspect is that depending on the grain size, we can vary the height or the impact speed, and see that the main aspect is that as the impact speed improves, the depth, the final depth or the greater depth of this fingerprint, it also improves. So this is a relation between a parameter that you can see and measure and a parameter of the droplet, which is the height. Also, the grain size, the initial height, we can see in this phase diagram, by this phase diagram, that just looking at the height and looking at the shape and knowing information like the initial height or the grain size, the type of the sand you are, the beach you are, for example, you can determine one parameter or other, grain size or height. Also, the final droplet diameter, which is what we measured, and it's here compared to literature, can also infer about the diameter of the height of the droplet by a linear relation or a power law, depending on the on other parameters of the droplet. As you can see here, which was done in this work, plotting the final diameter and also a theoretical relation which comprises the density of the grain and the density of the droplet and the Weber number. We can collapse the data. So our final conclusions are that there were two questions in the statement. One about the formation process, and I show here some very nice to see figures about how the formation process occur. You also has this pattern of an intermediate state and then the final form, and you can measure all of them in real time by the laser method, and also how the resulting crater parameters can be related to the inferable droplet parameters. Well, and that's it. Thank you very much.
All right, now we have 2 minutes for technical questions.
Thank you, Lauro, for your presentation. Please, can you back to your, I think, first slide, slide 4 or 3?
Sure. 4. 3.
3, yeah. These results are all from literature, right?
The right-hand side.
The right-hand side, yes. Your the analysis of literature. The crater depth.
Yeah.
Okay. Have you done any experiments besides that you showed us the graph on the left side?
Yeah, our self-made experiments were these showing in the left-hand side.
Did you do another experiments than that?
Not showing
comparing
here.
Diameter and the height, or no? No.
No, not showing here.
Okay. Does your graph has an uncertainty or not? I can't see it.
No, not showing uncertainties.
Can you explain
visualization?
Okay, can you explain better your setup? I didn't understand very well. Did you measure in the level of the sand? How did you release your droplets?
We used
Can you explain better your setup? You use this form to put the sand,
yeah.
But how did you release the droplets? Did you control these parameters to do this graphic? Did you use the same sand or changed it?
Yeah, we use a syringe, to
with a needle or not?
Well, unfortunately, we're gonna have to leave that for the discussion further. Okay, so now the opponent team has has 3 minutes. 3 minutes to prepare their presentation, starting now. All right, you have 1 minute. So if the captain for team Unicamp or someone could just tell me who will be presenting for team Unicamp?
Yes, of course. João Pedro will be the opponent.
Okay, thank you.
É isso. Mano, é isso. Tipo, começa por essa prioridade, essa lista de prioridade que tá boa mesmo.
Your mic.
I muted him.
Oh, sorry.
All right, so time's up.
Mateus, I host disabled participant screen sharing.
Oh, well, well, Henrique will make João Pedro as a co-host. Okay, Henrique, did you do it?
Oh, okay.
Thank you. So please try to share. Sorry, we only found out who was going to be the opponent afterwards. That's why it was a little hard to figure out. So the opponent's speech has 5 minutes. And you can start, let's see, right now. Yeah, if you want. Go ahead.
Oh. So I'm João Pedro Minquilo. I will be the opponent. I will don the opponents for Unicamp team for problem 10 droplets and the fingerprints. First of all, let us remember that. Oh my God, I did the wrong presentation. I changed my.
Okay, yeah, no problem.
Can we have a tactical timeout?
Okay, so a timeout means there will be 1 more minute for Team Unicamp. Yeah, okay. Timeout was given.
We have 1 minute.
Yeah, we added 1 minute to the time.
Can I start now?
Yes, sure. Go ahead.
Okay. So let us remember the problem statement. When droplets fall on a surface covered by a layer of sand, interesting patterns are formed. Study formation process. What parameters of the droplets can be inferred from the resulting pattern? So thank you for reporting. So let me point some positive points and negative points by his presentation. Some positive points that are they analyzed the problem statement, did a very good review of the literature with good articles and the good data collected from them. They identified the cohesion and the surface tension as an important parameter of the crater formations and show us beautiful figures with beautiful results of the craters. But there are some negative points and improvement points to his presentation, such as in slide 3, the lack of error bars in his graphics, the lack of clear experimental setup. We didn't understand very well how the setup was developed and involved. The lack of picture of experiments by the team and the variation of parameters, because this problem has a lot of relevant parameters, and you said it for us, but you didn't bear it down too much to analyze the formation of the phenomena. Did not introduce the Weber number. You just showed us, and we don't know how it affects the problem and what is its importance to the phenomena. Some confusing graphs in slide 90. You showed us one graph first and after another graph. I don't know if they are correlated or if they were from the same paper, the same article. some lack of theoretical prediction of parameters, and we did not show the parameters of the droplets that can be inferred from the craters. It was a point that the problem statement asked us, and I can't observe this in your presentation very clearly. So I think we have some points to discuss in our discussion, including how you can control your setup and the parameters of the problem, the parameters of your sand and of your droplets, and how these parameters can change the resulting crater and change how the effect will occur. Some improvements in your experiments maybe will give you better results, such as we can talk about that and find some suggestions and some points that we can obtain better results. The importance, we can talk too about the Weber number relevance to the problem. Why is it important for it, and for the procession to form the craters in the sand, how the sand thickness could be important in your problem. I don't know if it was varied and if it was analyzed, but we can think in some situations that it can be important, and even that the wettability of your sand, if it was hydrophobic or hydrophilic, and how it will affect the droplet in the impact of the sand. And we can talk too about why the cohesion force has a medium or little or high relevance in the different situations that you analyzed. I think it's a point that we need to clarify and to understand better how this cohesion force acts in the process to have this relevance. Thank you all for your attention, and thank you, the reporter team. I think
all right. So now we have 5 minutes of discussions between the two teams.
Right. Please, I don't know if I can see the Zoom, but can you see my screen?
Yes.
I think we can start reporter team talking about your setup, your experimental setup. How did you control your parameters and you try to vary them? Maybe I stop sharing my screen or not. Can you hear me? Who's team are here?
We can hear you.
I think Lauro lost his connection.
I saw her face stuck. Yeah.
Yeah. Okay. Well, we can. I think it's wise to stop the clock then, and just refill the 5 minutes again. And then we can start whenever he's back online, because Laura is the official reporter. So yeah. All right, let's just wait for him to connect again, and that's it.
I'm sorry.
Laura is back online.
Yeah.
Could you see my entire presentation?
Yeah, I watched it.
Okay. If you want to share your presentation,
okay,
you prefer.
Sure.
All right then, but okay, so we're gonna start the 5 minutes again right now.
Okay. Thank you, reporter team. I think maybe we can start talking about your experimental setup. Could you explain better, and again, how did you vary your parameters and how the setup was controlled and developed? And
yeah, sure. Well, to drop the droplets, we use a syringe with a needle, which is my appendix.
Very thin needle, like oh,
Yeah,
right, thin needle. Did you measure the diameter of the needle to have an
of the
estimate
needle?
Sorry.
No, what we did was to carefully see what's the volume of the droplet instead of its diameter.
Oh, so
we control it. We
Mhm.
mainly control. We chose to mainly control the volume of the droplet and to measure the diameters, the final crater diameters. We use this specumeter.
And did you so? Oh, now I can understand. Did the perimeter affect the measure of the diameter or not? If
No,
you
we
put
we
it
did not
inside
touch
of
it.
the sand, no.
Yeah, we do not touch the sand at all.
Right, but could you why did you calculate the uncertainty of the volume of the crater depth, the crater diameter?
Actually, the uncertainty is the perimeter uncertainty, which is actually here, right? This information.
Okay, the syringe, you handle it, you fix it with your hand and press it, right? Or did you use the I don't know, like a place to put it and to make it very fixed, very controlled, a support?
We use we measured the height and then we fixed it in without a method, a certain method, as you are saying, right? There was not a support, but we made sure that it was not like shaking, and we knew the height of it, like knowing where to put our arms or such like that, and then we drop it.
Oh, okay, so maybe it's a
was not
very
that fine
huge
control.
font to uncertainty. You maybe
exactly.
could shake and don't exactly precise add the syringe to your
Our
fixed
precision
position.
is
So I think it's a point that you
of some
could
centimeter.
clarify to your presentation, because I didn't understand that and I didn't know that.
Yeah,
but
it
I
was
think
a
we
choice.
can.
I prefer to talk about it in this
No
discussion.
problem. Yeah, well, I think we can talk about another subject. Maybe about the Weber number. Could you go to your slide that you talked about that? Why did you not introduce it? And could you explain better why it's your importance for the problem?
Yeah, sure. My intention here was to show that we can relate the height of which we drop the droplet and the final crater diameter. So I show this
graph
plot
at the left, right?
Which
You're talking about
the left and the right, both of them.
But this
here
graph
is kinetic energy, which is
kinetic
proportional
energy,
to
and what is your y-axis exactly?
It's height.
No, in the left graph.
And the left there. Yeah, sure.
Yeah.
This is the final crater diameter, which is D.
Final crater diameter under what? What is
annotation.
D0? Final fingerprint diameter. Oh, right. But what is D0?
Yeah. D naught is the droplet diameter.
But you said that you didn't measure your droplet diameter. You measured your volume. You calculated it from your volume.
This plot is from this reference.
Oh, okay. And you're another graph.
Comparing to my.
You're comparing with your own data.
Yeah.
Yeah. But this is in high and this is in kinetic energy and the
kinetic energy.
You can relate it, but it's not a
velocity.
All right, now all team participants can join.
Okay, could you show us your other graph about the Weber number? Did you relate this graph with the other two?
They are related. my intention here was to show that this kind of data, this exactly kind of data, can be collapsed in a same line by this modeling made by this reference here in this PRL.
Oh, you're talking
So
about
I'm
two
showing
different
the
references.
advance of this study. That's my only intention with this.
Okay,
No?
in this graph, you use the different sands and correlated the density with a graph that you didn't show us the density and the type of the sand. It's quite difficult to understand how these parameters are very different and how a lot of parameters can affect your graph. You are mixing different graphs that the data could not be correctly related. I think this is
That's a false impression.
That's
because
a false impression.
this is yeah, because
I think not, because you're correlating
based
Weber
on
number that depends on large number of parameters, such that density, surface tension, velocity of impact, and the droplet diameter, and you didn't show us the correct parameters of that to correlate one to the other. Maybe they are very different, and you didn't show us the
correlation
precision
between
data of
them
that.
is showing exactly in this graph, which collapsed the data into the same line by this modeling. So we model the problem, and then you get a relation between the final radius and the radius of the droplet and this value here. So you calculate this to each set of data of your that you performed the experiment, and then plot this in this kind of graph. When you do that,
now I understand
you find
better.
that all plots collapse to the same line, and that's
okay.
amazing.
I think we can move on. Leonardo Falabella wants to add something.
Yeah,
please.
Thank you. So just to clarify, this graph is from literature, right?
Yeah.
Okay, so could you explain what's the importance of the Weber number for this problem?
Well, in this modeling, the Weber number comprises the kinetic energy and other parameters relevant, like the surface tension and the impact velocity, then are inside the Weber in this case.
Oh,
but
I see.
other
And
models also in literature,
I just wanted to
I'm
clarify
informing you this because it's relevant to the question. In other modelings, the Weber number does not appear, but also a different combination of parameters and a different power law is also observed by other papers.
Oh, I see. Could you explain what is the ratio that Weber numbers is calculating?
Well, I did not put this here because that was not that relevant to my discussion.
Oh, I see. We as a opposing team disagrees with that. We think that Weber number is very important because we have other parameters of the droplet, like density, that isn't included totally in his model. However, I think Álvaro wants to make a question as well.
Yes, thank you, Leo.
Let me answer this comment, please. Well,
yeah, sure.
When you say the Weber number is important, you are considering that this is the only modeling possible, and that's not true because there are I found in literature other ways to model this. That's why I did not put the Weber number as a main parameter to this problem, because that's not a consensus in literature.
I didn't say that this is the only way to model, but we think it's an important parameter. But we like to move on. Please,
yeah, I'd like to move on.
Sure.
Thank you, Laura.
For sure.
Could you come back?
This axis, it is an important parameter. But okay.
Could you come back to your crater formation? I'd like to ask you a few questions. When you say that you have a diameter for the crater formation, do you see only one crater, or do you see like a little bit of sand outside of where the crater is formed? Could you come back to your images, please? I mean a secondary crater.
Like this here?
Yes. What exactly is that you measured? What is the crater diameter?
Crater diameter is showing in this figure here. It is the DC infinity here, up here. It is the outer diameter.
Okay. Do you think there could be an uncertainty related to where that is? I mean,
sorry,
a second crater formation. That's what I mean.
Well, the experiment is you have to wait until you get the final form, then you measure. And this kind of measurement here is very precise.
Okay, thank you.
Could you go to your slide about the, yes, this slide. Could you clarify exactly what is medium, very, and little relevance of the each parameter? I can't understand it, and it's quite...
I try to understand the physics of the problem basing on the types of force which are acting on the problem. So we analyze this in the following way. First, the cohesion force is responsible for keep the grains together. So it is more important if a sphere or sphere-like form is formed.
Okay.
So
the cohesion force is to maintain...
Unfortunately, the discussion time is over. So I would like to ask the reporter team to just give their final remarks in 1 minute, please. Go ahead.
Well, I'd like to thank you very much for this discussion, and also thank my teammates for helping me with this experiment, especially Yuri, which is in the title of this presentation. It was a very nice discussion. Thank you all, and all for watching too.
Well, all right. If the reporter team has nothing else they would like to say, then we move on to 6 minutes for questions from the jury. Jury members, please just raise your hands or start speaking up. And okay, Claudio Lenz, please go ahead.
Well, thank you very much to both teams. I have a question to the reporter team, which is this problem seems to be quite difficult to model. I mean, you need to take into account many things, and this is what specialized literature does. On the other hand, this seems to be a problem that is so easy to set up, even at home or in a laboratory, to get many different experimental parameters. So my question to the reporter team is, what were the main difficulties that you had in setting up a nice experiment and varying many parameters?
Mm-hmm. Yeah, that's a very relevant question. Well, first, the grain size not something that much to control if you are doing it in home and are not able to buy a very controlled type of grain. So that's a parameter which is hard to determine. Also, to make a study of the depth and the final shape of the fingerprint is something very hard to do. Once in literature, we see that they do this with a very specialized type of experimental setup, which uses lasers and very fancy technologies, which we have not in home to use. So that's also a difficulty to set depth and other parameters which are related to this. And for example, the intermediate states, which we can see in this figure. So that's very hard to study in home. This is an experiment which seems to be easy if you are if you wish to only measure height as a function of final diameter, or explore different types of shapes, but not exactly to determine precisely the parameters you are interested in.
May I suggest, I mean, okay, someone else wants to make a question, but I mean, you could, going around in a beach or in parks, collect sand, and you could use peneira to select sizes. With a camera and using lighting at different angles, you could maybe measure depths, for instance, and certainly shapes.
All right. So now, Professor Jeroen, please, could you ask a question?
Okay, I would like to thank both teams for the interesting discussion. So we are seeing this slide of conclusion. We are seeing this little movie. I guess this little movie is from this reference underneath. Okay, is that correct?
Uh-huh.
And is probably a bulk surface of sand. It's not a thin layer, right? This is just a surface of sand, but it's bulky.
Yeah, the layer has a deeper depth than the final crater depth.
Yeah, because in the statement you have a picture of a thin layer on top of a wooden surface, and in some droplets you could see that the droplet impact completely removed the layer of sand. So and then you see that there is only a thin layer of sand on top of it, and then I guess the physics is very different. So if you go back to the slide where you have the picture of your experimental result.
Here?
Yeah, on top there. And I can't quite see what is the regime, if it's like a bulky, like in the last slide, or is as in the statement, as the picture of the statement of the problem. So did you vary the thickness of the sand on the surface, or you have just one layer, and you think it's more like a bulky behavior, or is like the thin layer behavior? Can you elaborate on that based on your experimental results?
Yeah, that's very interesting. One very relevant point is that in modeling this, which was used to collapse all data in the same line, they use a model to a hard surface, which you drop a droplet in a hard hydrophobic surface and you see it bouncing. Use this exactly model to this problem, and you get a graph, a plot like this, which barely more or less collapse the data in the same line. So in this way, treating this as well, using this argument, I would say that it's not that relevant if this is a bulk or not phenomena because of this result. But for sure, a more deeper study on this will be very welcome.
Okay, so in this graph C, there is no sand, just a droplet on a surface, on a hard surface.
In this graph, there is sand. In this
on
data,
C?
there is sand, but the modeling is not for sand. Even the modeling not being for sand, it collapses the data to a line.
Okay, I have another. Yeah, I have a more technical question. How do you define you measure the diameter with a pachymeter, but the shape of the droplet is sometimes irregular, as I can see on your picture there. And how you define the border, okay, the line of, because you can have, as you said, you can have many different shapes of droplet fingerprints, the pancake, the truffle, so how you define the size of your crater, what was the reference that you used?
It was this DC infinity, which is the greater radius we can see, which
okay, I think.
Okay.
Yeah, I just said something about Lauro's comment. I think the Lauro's was a bit wrong in talking about the thickness. It was not important parameter. I think it's very important to measure the thickness and to control it, because as Jury said, the picture in the problem statement was a very thin layer of sand, and the regimes are very different, and you can have different parameters that affect the crater formation in that. Maybe the impact, the velocity will cause different results in a thin layer of sand, very thin layer of sand, and with a very millimeters more than that, we have a very different result. And I think it's not a quite difficult experiment to do at home. In this case, to varying the thickness, as Lauro said before to the other question. Thank you, Jury, and for attention.
Okay,
welcome back, Lauro.
Yeah, welcome back. You're still muted here, Lauro, but I think we can move on to a new question by Professor Ubirajara, and it will be the last question as well. Okay.
Okay.
So please go ahead.
Yeah, I was thinking about the results, and the reporter team showed put a linear fit, right, to the data. That's it. That's right.
Yeah.
I would like comments on both teams, if that's what you expected and why you did it. If for you, why you did it. If for both teams, if that's what you expected.
Mm-hmm. Well, in a certain interval of final diameter, we could expect a linear fit, mainly for small diameters, because actually what literature sees is that this relation is actually a power law, but they prefer to measure the total energy or kinetic energy. And for kinetic energy, that power law is something about 0.16, between 0.16 and 0.18, which is in literature. Also, other works presenting corrections to this also showed other power laws. So this study of power laws on this dependency on height and the final crater diameter is very interesting, and various papers worked on that.
I agree with Lauro that is an important graph, and the importance of the power law is because we can predict the crater diameter, and even the internal crater diameter, that is the wet crater with the mixture of the liquid and grains, and the external crater. And I think maybe the Lauro could obtain the results to do this graph, because it clearly gives us the important parameter and the importance of the important behavior of the droplets in the sand.
Thank you.
All right. Now the jury will decide our marks and send through the forms as previously instructed. So thank you very much for the nice discussion. Let's wait to see.
Well, I'm sorry. Where is the forms? Do you have a link for it or something? Or
yeah, they were sent through email, I believe. But I can see if I can share now with you as well.
I thought we were showing on screen like the captain's.
Yeah, no, like you're all gonna send, and then we're gonna compile, and then I'm gonna send here on the chat and comments on the grades and stuff. Yeah, that's how it works. Like, yeah, last time it was like that. So I think we're gonna keep the same format. Yeah. Oh, so did you receive the form already?
Yeah, I'm downloading it. I'm clicking on the link right now.
Wait. Okay. Cool. I'm also gonna send you again.
Okay. I'm on a form right now.
Okay, cool. Thank you. All right, I think we've received all grades. Let me just see. We're just solving here like the grades, but we already have all grades. We're just gonna tell them to you pretty quickly. Let me just access the spreadsheet.
Mateus, you will speak the grades or you send on chat?
Well, I think I'm also gonna send them on the chat. It's a little bit complicated for me, like right now.
Oh, that's fine if you only say it. We can write it down here.
All right, so first, I'm gonna talk about the grades for the reporter. So, Professor Alexandre, as a reporter, gave a grade 5. Obirajara gave a grade 7. Claudio Lenz gave grade 5. Ian Braga 6. Antonio 5. Yerum 6. And Claudio 5. Okay. And now the grades for the
Mateus, you count. Sorry, you counted me twice. I'm sorry.
Oh, did I count you twice? So okay, sorry. Yeah, okay. So yeah, but those are the same grades. Yeah, sorry. So now for the opposing team, Alexandre 8, Ubirajara 9, Claudio Lenz 8, Ian Braga 8, Antonio gave a 6, Yerum an 8. Okay, so those are the grades. So I would like just for quick comments. So on the does any jury members have any comments about the grades they gave to their team, to the teams? They can speak up right now, just for quickly just remarks. Yeah, you can speak anything you want, like,
Okay.
oh, why this grade?
I'll talk. So I gave the lowest grade for the opponent team, mainly because I felt that they only focused on the experimental aspect of the reporter, right? So for me, it was mostly stuck in this loophole of the experimental results from the reporter, and didn't build up onto how or what could be done to achieve the final question of the problem. And also in the end, I felt that it lacked clear information if the problem was actually answered or not by the reporter. So my grades was lower for the reporting team. Okay, thank you.
Right. If anyone else has any comments.
Yeah, I think in general, I thought that the reporter team could do I think that was clear. I think in all the comments, even with the opposing team, that they could do a better work in the experiment, trying to control better the parameters and show these things. That's why I think I gave a lowest score to the reporter team. The opposing team did a good job. I thought the fight was kind of a fight today. People mixing up, but that's the difficult to do this online. And otherwise, I think both teams did a good job. So just congratulate, but that's it.
Okay. Thank you. Well, if we have no more comments from jury members, then Claudio wants to speak again. Yeah, go ahead.
Well, I already mentioned this in the questions, but I think there was clearly a lack of experimental development by the reporting team. And I think the opposing team got to that point, but didn't. Maybe, as Antonio said, they could have emphasized even more that. Congratulations, anyway.
All right. Yeah, if we have no more comments for jury members, then we're gonna come back and okay, we're gonna come back in 10 minutes. You can talk during this time if you want, but if not, just please remain muted because it's been broadcasted. So yeah, use this time as you wish. So because I saw Leonardo wants to speak, so no, but let's just go for the 10 minutes break.
Yeah, of course. I just want to make a quick question. Oh, okay, I think Henrique knows the answer as well. Henrique, I just want to clarify if is any grade gonna be discarded, like the highest or the lowest, or we are considering everyone? Lowest. Okay, thank you.
The other fight is being broadcasted also or not? I think people are not. I received some message.
Yeah, overall, I liked the problem, even though using a homemade experiment with sand and dropping water from a commercial syringe you can get. I think that also, as Jeroen pointed out, the experimental aspect lacked a bit of rigor, right? Because, as was pointed out, the droplet size uncertainty was associated to the instrumental error. And since it's not a perfect sphere, a perfect circle, the droplet, you would have to have some other type of statistical error for the droplet radius, right? So I guess for the reporter team, this aspect also was important to measure, right?
All right. Let me just call everyone back. Just gonna wait until everyone shines here in the video again. I'm still eating my breakfast because it's now 8 in Canada. 9. It's 9. Almost 9. So yeah, as soon as the team member says that they're here again, I'll just wait a little bit more. This is some jury members offline as well. Maybe everyone is coming back still. Okay. I'll just wait for some more minutes. Are all juries here? Ian, are you there?
Yeah, I'm here.
Oh, okay, cool. That's because
Sorry.
No, it's just because before I was seeing you, so I was like, okay, maybe he's not there. I mean, are all teams here? Let's see. Team from USP, are you there? Are all team members there?
Yeah.
Oh, cool. All right, then I believe we can start the second round of our physics fight. All right. So I think we can start. So now the presenting team will be University of Campinas, Unicamp, and the opponent's team is University of São Paulo, USP. So yeah, please. The opponent team, USP, can challenge Unicamp in one of the problems. Except, again, just as a reminder, except for the problem that we just presented of the sandy droplets. So, yeah, you can move on with the challenges.
Okay. We challenge problem smashing spheres.
That's a tactical rejection.
Okay. We challenge problem number 2, air bounce. To the international list.
That's a tactical rejection.
All right. We challenge problem number 14, rising in the bulk.
We accept that challenge.
Okay.
Okay. All right, so Team Unicamp, you have 5 minutes to prepare your presentation. Who will be the presenter also?
I will be the presenter.
Yeah, Gustavo.
Okay, Gustavo will be the presenter. Let's see. Yeah, the clock can start. We didn't start the clock. Just please. Okay, nice. Just for the preparation. Let me just also read the problem. So if problem 14, rising in the bulk, if a vessel containing granular material is shaken abruptly, an item placed at the bottom will ascend upwards through the material and emerge at the top. Explain the phenomenon and devise the most energy efficient shaking technique to raise the item up. That's problem rising in the bulk. A lot of sand in this physics fight, right? Interesting. All right, it reminds me of a problem in 2019 that I had to deal with. It was pouring sandcastles. A really nice fight. You can even watch that online. It's on the International Physicists Tournament channel on YouTube.
Won.
What? Sorry?
Nice because you won, or no?
Yeah, I mean, yeah, that round, yes, we did win. We did win. Yeah, it was nice. I can even tell you a story about that. I finished the presentation 2 minutes before I went on stage. And it was pretty cool. Like, it got like interesting grades. Like, it was like 8 of average or something like that. So it was a really good one. I was not expecting that, but I was really happy. Yeah, but I did talk a lot in that fight, just, defending the solution. Yeah, it was a nice experience. Yeah, you'll see that at some point the projector even stops working. Well, yeah, set a good example. Yes, okay. So, yeah, I should not say I finished the slides 2 minutes before. So.
Well, I'm ready. Can everyone hear me? My audio
Yeah.
is okay.
Wait, can you share your screen too? Can you screen share?
Sure.
Oh, okay.
Just 1 second. Let me.
Yeah, no problem. You have more than 1 second. You have 2 minutes and 20 seconds.
Okay.
All right, so you can start your presentation.
Just
now.
1 second.
Oh, okay. Yeah.
So I'm ready.
Okay, so you can start now, please.
Hello, my name is Gustavo, and I'll be presenting problem number 14, rising the bulk. So first, the problem statement. If a vessel containing granular material is shaking improperly, an item placed at the bottom will ascend upwards through the material and emerge at the top. Explain the phenomenon and devise the most energy-efficient shaking technique to rise the item up. So first of all, on left, you can see the video, top view of the phenomenon, where we see a ball rising up right now, and we'll call this ball the intruder. So some first impressions about the problem. We noticed that the granular material resembles a liquid, and it's very easy to do the experiments by hand. So we devised the following experimental setup. The setup consisted of a container, a solid base, and a cell phone accelerometer that we use to get the data using the software Firefox. With that setup, we achieve a pretty good result of acceleration, shaking by hand, and a relatively pure frequency for our experiment. So to define some basic parameters, the most relevant parameter that I will talk about is gamma. I would define gamma as being the ratio between the maximum upwards acceleration divided by gravity. For a simple harmonic oscillator, that's it's approximate our case, gamma will be the amplitude of the shaking times the angular frequency squared divided by gravity. If gamma is greater than 1, the particles will move away from the container and will be able to rearrange. So that's what we want. Then we can define that a particle will rise if and only if another particle sneaks in underneath. This can be done by 2 distinct mechanisms, the convection currents and the percolation-like movement. The convection currents happen due to the friction between the particles and the boundaries. You can see on the image on the right that the particles near the boundaries rise less and create vacancies that can be occupied by the neighbor particles, just like the GIF shows. To observe this convection currents, we painted grains of corn in different colors and stacked them by layers, just as the image shows. And after shaking it 5 times, we can see some interesting results. First of all, we can see that the blue layer apparently volume has increased, but that's not the case. It just changed shape to a hollow cylinder, evidenced by the image on the right, where you can see that the white grains started to emerge on the center. We also noticed that the black layer and the yellow layer moved down, and the yellow layer started even to enter in this hollow cylinder, which confirms that the convection currents do exist. And to test these convection currents, we replaced the container walls with sandpapers, and with that we found that the increase in the friction between the layers, the wall, and the grains had made the time to rise of the particle, given a constant acceleration, to decrease, just as expected. So now the percolation-like movement. In the percolation-like movement, the intruder goes up. create vacancies that can be occupied by the granular material on its surrounding. And we can say that the percolation-like movement makes the intruder goes up because it's just more likely for the intruder to create gaps that the grains will fill. Then it's then a bunch of grains to move in unison to create a bigger gap for the intruder to go down. So to observe this phenomenon, we devised this following pseudo 2D experiment where we can see the ball at all times, and devise the following graphs showing the number of steps being the tap, the shaking motion against the intruder height. And we can see some pretty interesting results. First of all, we can see this step-like function that the intruder has, and we associate this with the percolation-like movement, where the bigger the size of the gap is dependent on the amount of grains that fill the vacancies left by the intruder. We also observed some rising with constant velocity, and we associate this with the convection currents because they happen pretty much frequently. And we also noticed that once the convection currents happens, the percolation seems to stop. So now we devised the most energy efficient shake technique as the one that spends the least amount of energy to make the intruder rise. In order to create this, we will take a statistical physics approach. First, we divide our container in d by d by d cells and assume that we have a fixed number of particles, that 2 grains cannot occupy the same position in space, which is a fermion-like behavior that would be clear in a moment. Grains motion must not be restricted at the top of the vessel, and our shaking amplitude divided by the grain diameter has to be greater, has to be smaller, way smaller than the number of layers, given by me just as the image shows. Now with this assumption, we can treat the problem like with Fermi statistics and assume a Fermi direct distribution for a temperature different than 0. Just as with a temperature greater than 0, we will have particles above the Fermi energy, which now our me. With that in mind, we can now equate our kinetic expansion with this analogous thermal expansion to create an analogous temperature for our system, which is given by the following equation. And now, given this thermodynamical approach, we can now devise the fluid phase as being a phase that the particles move more freely, have a lower density, and behaves somewhat like a fluid. And a solid phase where the particles move, just wiggle around its center of mass and does not have any significant movement. With that in mind, we can now hypothesize that the phenomenon only occurs when the system is fully fluidized, because only then we will have the possibility of creation of gaps that will create the both mechanisms that I talked about earlier. And with by equating the energy necessary to do that with the thermal energy, we can arrive in this following critical temperature for our system. Now we can update our condition for the phenomenon to happen. Before we had that gamma has to be greater than 1, which is not sufficient to describe the whole system. Now we have a complete description when the temperature of our system is greater than the critical temperature. To test that, we first shake the container horizontally, that in our understanding does not increase the temperature of the system. And as well as the same way as we expected, the horizontal shaking does not make the particle to go up in any way, just as like this video shows. Then we use the same 2D setup, but now we vary the number of layers of our experiments and observe whether the intruder rise or not. And with that, we can now predict the maximum height that a given temperature will make the intruder go up, make the phenomenon happen, basically. And we predicted a height of 8 plus or minus 2 centimeters, and we measured a height of 8.5 plus or minus 0.5 centimeters for that temperature, for this temperature here. And it's a pretty good result. So now, to recapitulate, the most energy efficient shake technique is shaking the container vertically and create the smaller gamma possible, such that the critical the temperature of the system has to be greater than the critical temperature. So some general conclusions: the friction between the boundaries and the grains are a relevant parameter for the convection currents, and the convection currents are way important than the percolation-like movement, for the intruder to go up. We also defined the most energy efficient shaking technique consists in the shaking of the container vertically and make the temperature just barely above the critical temperature. These are my reference, and thank you for listening to my presentation.
Right. Now the opponent team has 2 minutes for a technical question.
Could you go back to slide number 15?
Oops, I'm sorry, I stopped sharing. My bad. 15? This one?
Yeah. Could you explain what's the point of tracing these dashed lines?
Just to show that the dashed lines show the tendency of the particles. Here you can see that the height remained relatively constant, and then the height increased in a pretty constant rate. This is to allow us to show how the percolation and how the convection currents will behave in our system.
Okay, and could you explain where do you define the height of the intruder? Like, what's the
center
what's
of
the
mass.
reference you use? Okay.
We assume a homogeneous ball to calculate the center of mass.
Okay, could you go to the slide where you introduce the Fermi statistics?
Yeah, this one. Or the
Oh, sorry,
one?
the second, the critical temperature. The critical temperature.
Okay, at the critical temperature here.
What is G?
G is the gravity acceleration.
No, sorry, D of.
D is the grain diameter. I define it here.
All right, time's up. So now the opponent's team has 3 minutes to prepare the presentation. Starting now. Hi. So also, who's going to be the opponent so that we can put it as a co-host?
Me, Bruno.
I think it's Bruno, right? So, okay. 5 seconds.
Okay, I will share my screen.
Okay. So the opponent team has 5 minutes to make their presentation. So please, starting now.
Okay, so hello everyone, my name is Bruno. I'm from the USB team. I'm going to be opposing problem number 14, rising in the book. So just to quickly remind the statement of the problem. If a vessel containing granular material is shaken appropriately, an item placed at the bottom will ascend upward through the material and emerge at the top. Explain the phenomenon and devise the most efficient shaking technique to raise the item up. So there are two. The main task is to explain the phenomenon, and secondly, to devise the most efficient in energy. So the positive aspects, which are very strong, are creative experimental setups. So, for example, the idea of changing the color of the granular material to detect the convection was very useful to understand the problem. And the analogy with statistics, they use statistical mechanics to model the problem and understand better. So this was very important because it's not a simple problem to study deterministically. So this is a very strong point. And they also predicted the maximum displacement given with a given parameter gamma. And also there are some other positive aspects. For example, they used they defined specific quantities such as the alpha or other non-dimensional parameters to help that are more appropriate to model the problem. So this was very useful too. So there are other topics that we would like to clarify or better discuss. For example, what is exactly the condition for occupying the vacancy? Like you showed, like if in the first slides, I think the fifth slide, there was an if and only if condition, and I would like to see this more carefully because this is a very strong claim, and I mean maybe it should be prior experimental investigation before introducing this claim, or at least mentioning it after through the experimental investigation, like we are doing this to because we assume that if and only if condition. So I mean this is just to safely accept this condition. And the other topic is is the item shape. Like how does the phenomenon change if you change the item shape? If it's spherical, if it's a cube, if it's a amorphous solid, or maybe this is a relevant parameter, or it's not. So and if not, why? So this is we would like to discuss that, and just we also would like to see better what's the relation between the gamma factor and the displacement, because I mean the acceleration, the shaking is very quick. So but I don't think the acceleration is constant, or I mean if you are assuming this is constant, so gamma is an average acceleration. I would like to this to be clarified. And Also the percolation, so seeing the ball influences the 3D movement, restricting 2D movement. How does it influence the phenomenon? As like if you yes, if you shape one way or horizontal, what would you if you mix the two components, how would your parameters change? And what's the experimental way to analyze the critical temperature? Because I mean, this is a more statistical temperature, like you don't measure with a thermometer. So how do you approach this temperature? Because I understand this is a very important parameter, because you mentioned this sometimes. So yeah, these are the main points I would like to discuss. And also,
all right, now the teams have 5 minutes for discussion.
Okay, can all of you hear me?
Yes.
So
maybe you can share your
sure.
first screen. Okay.
First of all, I would like to comment on the condition that you said that you need for the clarification. Well, what I'm saying is that because an item has to be on top of something in order to be on the height, it will only rise up if another thing sneaks in underneath it. So it's just saying that the amount of stuff underneath it change to a greater value. Does it make sense now?
Yeah, but how does it change with the amount of granular material that is on top of the item? What's the relation between the vacancy on the bottom and vacancy on the top?
Well, I can certainly answer this, but that's not what the condition is saying. Just to clarify, I'm saying that we need something to enter underneath it to make it rise. Because otherwise the ball would just fall back to his place. So independent on the amount of it, the rising of the intruder, it won't stay there if another thing enters underneath it. So
okay,
does it make sense now?
Yeah, it's more clear. But it seems like there's something more to consider besides the what sneaks underneath. Maybe we should consider what goes around, like in the horizontal section. Is this important or not?
Well, I don't think that's important. Yeah, I don't see how that's relevant to our phenomenon.
Yeah, because where does the granular material come from to occupy this vacancy?
It comes from the sides.
Around.
But the dynamics of the side is not important for it to rise up.
But would it be difficult to also develop some statistical approach to the around of the item?
Well, I believe that
they are related, of course.
Yeah, they're related. I believe that's possible, but that's not that relevant for the understanding of the problem. That it's our main point. So I would like to move on. You commented on the shape of the container, the intruder.
Shape of the item, yeah.
Yeah, I totally agree. That's a very important parameter, but it's not relevant to explain the phenomenon. I don't need the shape of the intruder to make good observations and predictions on how the system will behave in a general way.
Mm-hmm. Yeah, I mean, the shape, after you said that, I think that the shape of the item, the shape of the intruder itself is not that important to understand the phenomenon. But I mean, I think that the shape of the item and the shape of the granular material need to have some kind of relation in order to the phenomenon happen. Because let us suppose they are all cubes, like the granular material are cubes and the item is a bigger cube. So there won't be any, you see there's a link between them. So how do you approach this dependence on the item shape and the granular shape? Because this is relevant. Otherwise, there are some combinations in which the phenomenon doesn't happen.
Yeah, we took this on the relevant on the critical temperature. In this condition, mean naught is the depending on the packing density and the packing density. As you said, when it's when the shape of the materials fully occupy the space, that's what we were saying. We have basically a lock mechanism that does not allow, as you pointed out, to make rooms for gaps to be created.
Okay, and how, I think the last, maybe the second to last point to discuss is how do you experimentally approach the Fermi temperature? Well,
I define the Fermi temperature as this temperature-like characteristic of our system. It's not the temperature, as you pointed out, but we do not measure it. We predict it by, it's a function of the grain mass, the grain diameter, and gamma, and the angular frequency. So we have these measurements, and we can predict our temperature as well as our critical temperature without a need for, as you said, a device to measure these characteristics.
All right, now all teams can join the discussion for 6 minutes.
Yeah, is the gamma, is the angular velocity related to the gamma? I'm not sure how do you.
Yeah, I defined gamma, and gamma is the, for a simple harmonic oscillator, which is approximately our case, is the angular frequency squared times the amplitude of shaking divided by the gravity.
Okay, how did you control the amplitude of shaking?
Well,
was there a systematic way to shake it properly? Did you use have you used proper experimental apparatus for shaking the device?
As I said, shaking by hand achieved a pretty good result. We can see that our max acceleration upwards is pretty constant, having a small uncertainty. So there was no need for a device to control these parameters.
Okay, I think Lauro has raised his hand, so Lauro, go ahead. Lauro?
Well, I would like to know if one small question about your one important parameter of your modeling, which is the temperature. It was an interesting idea to compare to a Fermi liquid, but I think it's not that clear, the meaning of all those parameters. Well, the temperature in this case and the critical temperature is analogous to which parameter of your experiment?
So just to recapitulate, you asked about the temperature and the critical temperature, right?
Yeah, both of them.
Okay, the temperature, it's analogous to in our system by equating the kinetic expansion of our shaking, so how much the center of mass dislocated with our shaking, and we said that this is not because of the shaking in our analogy, but because of a thermal expansion. And by doing that, we can now isolate the temperature to create this expression. And this expression is given by, as I said, the grain mass, the grain diameter, and this h naught function that is the maximum distance between a single particle and the vibrating plate. And it's a function of gamma, this h naught. I'm sorry, and you asked about the critical temperature. So the critical temperature, it's we calculated by calculating the amount of energy to fully fluidize our system. So when our system has the thermal energy equal their potential energy in the Fermi analogy, we will say that this layer is fluidized. So we calculate the fluidization energy for the whole system, all of the layers, and with that we have the critical temperature for our system to be fully fluidized.
But you did not follow the analogy to calculate a Fermi temperature.
I don't think I understand your question. Can you clarify a little bit more?
Well, you're talking about Fermi bath, so you're interested in quantities like the Fermi temperature, which you could have followed by your development calculator too, but you used another approach to calculate the critical temperature.
I'm not sure if I understand what you asked about. This is our temperature of the system and is given by the Fermi statistics. This is another piece of math development that calculates the energy for fluidization of the layer.
Okay, no, that's okay. I think
okay.
the this comparison to a known problem in physics is not very clear to me in the presentation, but it's an interesting idea. Thank you.
Well, if you give me time to clarify, I can. These are assumptions, and these are the same assumptions for the Fermi statistics. So that's why we can do this approach. So it's just an analogy based on our assumptions and how the model will work.
Now, Matheus, I think.
Yeah, so in the beginning of the presentation, you mentioned you modeled it after a simple harmonic motion.
Yes.
That is a periodic motion, especially one important factor for this movement is the displacement, the physical displacement of the object. How do you guarantee that the displacement is equal or the average is equal for you to consider a simple harmonic oscillator? Do you do that? For example, you're shaking it vertically. How do you define like the rest moment and how much the containment moved upwards and outwards? Did you measure that to clarify why did you consider it a simple harmonic oscillator?
Yeah, using the Firefox software, we obtained the data of accelerometer in all axes, and we can see that it matched a simple harmonic oscillator. But we did it only by hand. So, and we did this graph just to show you that it's possible to do it in a controlled manner by hand, without the necessity of any other piece of engineering.
But do you have a one about frequency, one graph about frequency, and another one about acceleration by time? But well, exactly, the displacement is very important for a simple harmonic oscillation. How do you
Sorry, the time is up, unfortunately. So now we have final remarks from the reporter team.
Can I start?
Yeah, go ahead. You have 1 minute for that.
I would like to thank you, the USP team, for the fight. It was a pretty good fight where I clarified all the points I needed for my system, for my problem development. And it was a pleasure to be here with all of you listening. Thank you, everyone.
All right. So now the jury can ask questions for 6 minutes. So please go ahead, jury members. You can ask away. I ask everyone to raise their hands if they can so that we organize it better. But yeah, we can start the question period right now.
Hello, Gustavo.
Hi.
I want to ask you because, in fact, I don't think that you had find the most efficient way to shoot. Because as I understood, you are saying that the main mechanism that goes the ball to rise is the convection. So it's why you're looking for the fluidized dynamics, yeah?
Yes.
Okay, but
I'm sorry. Let me just clarify. I also look at the fluidization of the system, because in the solid phase, particles will not move. They will be just vibrating like around the center of mass. So it's impossible in the solid system for the ball to go up.
Okay. And you find that the lowest energy that you have to do for the system to make the system is to be in this state is the energy that's the most efficient. But you know, if sometimes you give twice as energy and the ball rises twice as up, it's not going to be some case like that.
Let me, if I understand correctly, you were saying that if I have a bigger gamma, a bigger acceleration upwards, the ball will rise faster.
Yeah, faster, and with you know some most hate from it will rise more than with it will rise with the lowest energy. I don't know.
Yeah, I agree. I agree that
we
did the experiment, and with a greater acceleration upwards, the ball rises faster. But in my understanding of the problem, the problem is not asking for this. It's just happening for the least amount. In our understanding, our definitions that we have to we need the least amount of energy just to make the intruder rise. So the amount of time is not important.
Okay.
All right. So we can move on for another question by Claudio Lenz. Please ask away.
I have a question to the reporter, which is you show the harmonic motion and you measure the acceleration with 5-Fox, and from that you can get the amplitude as well. That's very, very, very nice. Very nice FFT, so you can really control the frequency as anybody expects. But did you change the amplitude? That's a bit harder, no? If you change the amplitude of the movement and the frequency changes as well. Did you do many experiments with different amplitudes and frequencies, or?
We did vary the frequency, but the amplitude was a bit harder to vary, as you said, because of this experimental part, but because we had this necessary condition that the amplitude has to be in the same order of magnitude of our grain diameter. So this does not leave us with enough room to vary this manually.
Okay. And a second question has to do with the previous question, which is maybe going slowly in one direction and fast in the other, not a harmonic oscillating mode. Would it be more efficient or not? Did you approach this issue?
Well,
was not.
Yeah, thinking about
actually, this is a question for both teams, actually.
Okay, so in my understanding, the only important thing is the acceleration upwards of the shaking technique. So in my understanding of the problem, the shaking downwards is not as important. So I think, but I would have to make more tests to be certain that we can model this greater acceleration in one direction by just modeling as a simple harmonic oscillator with a greater acceleration. Like the first part of the movement will be another harmonic oscillator.
So I mean, could you save energy if you go in one direction in one way and the other direction in another way?
Well,
also for the other team after you.
If you are doing it faster on the way up, I believe you would spend more energy in our definition of making the item rise up, and the rising down is not important. The shaking down is not important.
All right, now the opponent team has something to add.
I just would like to ask Professor Claudio to repeat the question because I think I missed the beginning.
Okay, he showed a harmonic oscillator. So the same way you go up, you go down. My question is, if you went up in a certain acceleration or whatever movement and down, for instance, very slowly, quasi-adiabatically, okay, would you expect a change in efficiency in making the ball rise up as a function of energy you spent?
Yes, I think so, and I also think that if your acceleration up is greater than your acceleration down, the vacancies will be the bottom vacancies will be occupied more rapidly. So I expect that the item will move up faster, but more efficiently. But I think that it's a limitation of the approach the reporter team used to approach the problem, because they already assumed the motion as a I mean, they considered the motion as a harmonic oscillator, and then calculated the most efficient, energy efficient way for this for this motion. But the statement of the problem didn't mention like to be restricted, didn't ask to be restricted to harmonic motion. So I think if you your acceleration up, it's worth investigating if you, for example, shake the your container with an acceleration up greater than acceleration down, it will like change the efficiency to.
Okay. Okay, thank you. Now, Professor Alexandre, please, one question. Just one question, because also we have Antonio to ask as well.
Oh, okay. So from your graph for the experiment, it seems you have two very different regimes, right? So you start from a metastable situation, and you have to drive your system to accommodate, and then you start to rise up the ball, and so it seems that your model, which is very nice, actually models very nicely the second part of the experiment, but not the first one. And you're spending about half the time in that region. So how would you? So it seems to me that it's not necessarily true that the most efficient solution for the second part is also the most efficient solution for the accommodating part. So how would you actually treat this part of the problem as well?
Can you clarify again the last part of the question?
Because it seems okay. So you use a very nice model, but the system is already in equilibrium. So you start from a sort of an equilibrium situation, which is really when you're trying to rise up the ball. But the first part is where you're actually accommodating the system into the lowest energy solution. So you're shaking the glass vials so that the ball, the sand that is around, or the grains that are around, are actually settling. So you're going from a metal stable situation to the kind of a ground state situation, and then you're starting to rise the ball. So do you think that the same model that you use for the rising ball is actually also going to give you the most efficient for this region of the graph up to about 15 steps?
Well, I believe our solution for the second half, as you said, actually describes the first part, because here we have a gamma that fully fluidized our system. So the system here is this motion is only happening because the system is fluidized. Because if it was not fluidized, the particles will not create vacancies. So this once the system is fluidized, now the percolation and the convection currents explanations kicks in, and we have this step-like function because the percolation like movement is a random process. Where we have a certain probability that this vacancy will be occupied. So this is why we have this plateau, and then it rises, then we have a plateau, and then the convection current kicks in, because we believe that in this specific container, in our shaking parenthesis, the convection currents only went to a height about 3.5 centimeters. Does that answer your question? I'm not really sure.
Well, I hope it does, because we don't have much more time. So now, please, Antonio, ask away.
Hello, nice presentation. I'd like just to give a quick, simple question. Since the problem statement asks for an energy efficient process, I'd like to hear from the reporter and the observer, how would you define what is energy efficient shaking technique? What is an energy efficient?
Well, we define the energy efficient as being the least amount of energy for the phenomenon to happen in any capacity. So if we have this condition that the phenomenon has to happen in any capacity, we then can calculate the least amount of energy that we need to spend for this happening.
I would approach this differently. I would say that the most if the energy efficiency here would be the ratio between the energy necessary to take a certain step of the item divided by the energy you used to shake the entire container. So this would be the efficiency I would define, because and then you control this, you analyze this quantity, this efficiency the way I said, like the ratio of these two energies, and try to maximize this with various parameters. The most relevant parameters, for example, the amplitude of the shaking, the size of the granular material, the mu coefficient, and so on.
All right. Now, thank you all for questions. I think no one else has questions, right? So we will go for the decision of the marks by the jury. So yeah, juries, you can decide their marks. And meanwhile, you know what the song is, right? Shake, shake, shake. Shake, shake, shake. You can do it very well. All right.
Mateus, I guess you have to be careful to broadcast music because the fight is being broadcasted on YouTube, and YouTube can take it down if you have a song with a copyright.
Oh.
Yeah,
Okay.
it happened with a professor. He was teaching a class and asked the class to make one exercise, and he put some, I think it was a Beatles song, just for the mood, and the class was taken down from YouTube because of that.
Oh, I'm really sad.
It's
right?
just, yeah.
So YouTube, if you want to take this down, take it down, you know, but I will put my music will be happy, you know. I guarantee our 10 spectators will be mad. But you know, I just hope not. Yeah, maybe they didn't even hear it. I don't know. I hope they don't take it down. Let's see.
It was just for a little bit.
Yeah, I know that there's something like you could put it like every 30 seconds sometimes, and it's something like that, and it's cool. Let's see. All right, we do have the grades. Wait, it's a little bit confusing for me. Okay, no, it's okay. So I'm gonna tell you the grades first for the reporter team. Ubirajara gave an 8. Ian Braga gave a 7. Jeroen gave a 7. Alexandre an 8. Antonio gave a 7. And Claudio Lenz a 9. And for the opponent team, Ubirajara gave an 8. Ian Braga an 8. Jeroen gave a 7. Alexandre gave a 7. Antonio gave a 6. And Claudio Lenz gave a 9. So now, if you want to talk about comment about your grades, please. You can talk away. Yeah, Jeroen, please go ahead.
Yeah, I would like to explain. I thought the work by Unicam was very nice, but I think it has two main problems. First, it looks like that there is no literature. So granular convection, it's a very well-known phenomena, and it's very important for food industry. And as you go through the presentation, it looks like there is nothing out there, no comparison with other results. And just on the comments, I saw that you cite some papers on the bottom line, because at first I thought you came up with the statistical mechanical model, but now I guess you took it from the literature, right? But this is not even clear. So it's like it's devoted from the connection with the literature. And the problem asks for an efficient way for shaking. It's basically how you build a shaker that will make the process efficient, right? And you go from acceleration through your presentation to a more abstract parameter, which is the A temperature. So, and then at the end, if you ask an engineering, can you build a shaker with it, and based on a very abstract parameter, which was very hard for everybody to understand. So I think you have to connect back on how you actually build an efficient shaker based on that model. Okay, if I shake it vigorously horizontally, is that a high temperature or not? That's not clear. Okay, I think this is and at the end the team actually shake it by hand. Okay, so I don't think that experimentally I don't think this is very sound. You have like experimental set data based on shaking it by hand. Okay, this was my comments on that.
Yeah, Antonio, if you want to ask something, say something.
Yes, I enjoyed the presentation from the reporter, the work developed, the experimental setup, and the model that was present in literature that they applied for their problem. But the only drawback that I gave a lower mark for the reporter was on the presentation side, because it went extremely fast. Some steps were not so clear, and in the end you had nearly 2 minutes still to finish your presentation. So that's why I scored a bit less for the presenter. And in the reporter, I guess you got stuck a bit on some issues, but even though identifying other key issues that was lacking, like the optimization of the perturbing part, that was not fully explored, you know. And that's why in the end I asked the definition for what is energy efficiency, because in the end you can also look at this from the thermodynamic point of view as entropy, right? So you have a very disorganized beads within the sand, and as you shake, you're applying external work, thus reducing the entropy and having all these organized beads on top. So there was some amount of work to overcome the potential energy. So the efficiency here would be the potential energy the bead has to rise against the work you needed to input, right, from your manual shaker. So for me, there's nothing wrong from the manual shaker, but I felt that it lacked some quantification of what was the efficiency and what external factors actually affected these efficiencies. Thank you.
Now, please, Claudio Lenz, you can ask.
I enjoyed very much the mixed colored corn grains. That was beautiful, right? And congratulations, that's fantastic. I think the opponent got to the very nice points as well. That's why I gave the same grade to both. I think the reporter could have done a slightly better job than this manual shaking. It's nice to know that you get a very nice acceleration, a very nice Fourier transform, but it's difficult to vary things, to vary amplitudes and so on and so forth. So I think maybe there are easy solutions at home, even with a bicycle, or and tying down the cup on the bicycle, on the pedal, or whatever, on the tire. I don't know. Even if you don't want to do a rotation to linear movement. But I think there are easy solutions so that you can get a much better control over the acceleration and quantify the energy spent and the efficiency. But congratulations to both teams. Very, very nice.
Do we have any other comments by jury members? Unfortunately, I don't know if I can comment on anything. I don't see anything else.
I forgot to comment on the opponent. Okay, and I think it's basically the same flaw that they did not comment on the connection with the literature. Okay, for sure, there's a lot of literature out there, and that they could correlate the work and the results.
Interesting. Yeah. So, well, after this, then I think we're done. We will now have some time for lunch. Henrique, you can shine and say so. Thank you all for watching. This was the first round of physics, the first physics fights for the Brazilian Physicists Tournament. We're gonna have a second fight in a few hours. It's gonna start. Let's see. I just go here and see that it's gonna start again at 2 o'clock until 4 o'clock, and then tomorrow morning again from 9 to 11, and the final will be from 2 to 6. Thank you all for watching through YouTube, and yes, we'll see you again soon. Hopefully, if you watch all the physics fights. But yeah, thank you all for participating. Hey, clap, everybody clapping. Cool. Yeah. Pronto, agora vamos falar em português, né? Já acabou. Já parou a transmissão, Henrique?
Só uma
Henrique,
dúvida.
você está mudo. Ah, peraí. Não, eu perguntei se já acabou a transmissão. Não tem problema, não. Um abraço aí, ó, para minha mãe que está assistindo.
Eu acho que o pessoal no YouTube não está me ouvindo, que eu estou mutado aqui, mas obrigado aí por todos assistirem. Obrigado, mãe do Matheus, aí por assistir também, e vamos encerrar. Né?
Isso. É isso aí, o Gustavo ia perguntar alguma parada.